Good day. Today we'll talk about Introduction to Quantum Physics. The topic is all about quantum theory. We'll learn today the basic domains of physics, the quantum theory itself, and the foundations of the theory. This slide shows the basic domains in physics organized by two main factors, namely the size and the speed. So as we can see here, on the vertical axis, we have the size of objects. So larger objects like planets or everyday items, just like your bags, for example, fall under classical physics. But when we deal with very small scales, around atomic or subatomic level, we move into the realm of quantum mechanics. So on the horizontal axis, above this table, we look at speed. When objects move much slower than the speed of light, and that is 3 times 10 raised to 8 meters per second, classical mechanics or quantum mechanics apply. However, when speeds approach the speed of light, we must consider relativistic effects. So combining these two main factors, we have now the four domains of physics. The first domain is the classical mechanics. This is for large, slow-moving objects. The next one is relativistic mechanics. This is for large objects moving close to speed of light. We have quantum mechanics. This is for tiny, slow-moving particles. And lastly, quantum field theory, which deals with very small particles moving at relativistic speeds. So each domain helps us describe the physical world accurately depending on the situation. But for this lesson, we will be dealing with quantum theory. All right, let's talk about quantum theory. Basically, quantum theory helps us understand how matter and energy behave at the atomic and subatomic levels. That means really, really small things like electrons and protons. Quantum is a word that means very small or very tiny. So that gives you an idea of the scale we're talking about here. At this level, normal values or normal rules, about classical physics, Newtonian physics, don't really apply anymore. Things start to behave in strange and fascinating ways, and that's where quantum mechanics comes in to explain what's going on. So, quantum theory deals with the very small, very tiny at the subatomic level. Now, quantum theory didn't just come from one person. It's actually a combination of several key ideas from different scientists. So for example, it all started with Max Planck in 1900s. He discovered that energy isn't a continuous thing or object, but comes in tiny packets called quanta, singular quantum. That was a huge shift in thinking. Then in 1905, Albert Einstein expanded on that idea and proposed that light itself is made up of these packets of energy, which we now call photons. Next, in 1924, Louis de Broglie introduced the idea of wave-particle duality. He said that subatomic particles like electrons can behave both like particles and waves, which was a pretty mind-blowing concept at that time. And that's why we now have the term matter wave. Finally, in 1927, Werner Heisenberg came up with the uncertainty principle. He showed that it is impossible to precisely measure both the position and momentum of a subatomic particle at the same time. The more accurately you know one, the less you can know the other. So all these ideas together form the foundation of quantum theory as we know it today. So why develop the theory? What's the reason why quantum theory exists? The first reason is, well, it turns out that laws of classical mechanics do not apply at the atomic scale. Classical mechanics, the ones that explain how big objects move, just don't work when you zoom in to the atomic scale. Things behave very, very differently down there at the subatomic scale. One of the big clues came from something called the photoelectric effect. Scientists noticed that shining light on a metal surface could knock electrons out from that metal surface, but the results didn't match what classical light theories about classical light predicted. So they found that increasing the intensity of light didn't always make more electrons come out. What really mattered was the energy of the light, specifically its frequency. Um, that strange behavior couldn't be explained by classical physics, and that's what led to the development of quantum theory. Now let's talk about the foundations of the theory. Specifically, we'll begin with Maxwell's theory of electromagnetism from 1864. James Clerk Maxwell came up with a unified theory that connected electricity and magnetism, showing they're actually two aspects of one fundamental force. That force today is called electromagnetic force. His work is summarized in four equations. Later, I'll be showing you not the equations themselves, but the meaning of the equations. And this is now known as Maxwell's equation. And they're among the most important things in physics. They help us understand everything from how light travels to how electric circuits work. The theory of electromagnetism, it states that electricity and magnetism are two different manifestations of the same force, the electromagnetic force. Maxwell's theory is described by a set of four equations. Let's talk about the equation summary, not the equation themselves, but the summary of the meaning of the four equations. The first one is electric and magnetic fields are always created together. Whenever electricity is created, magnetism is also created. Whenever magnetic fields are created, electric fields are also created. Electric and magnetic fields can travel through space as waves. So from a nearby star, for example the sun, when electromagnetic waves are created, they can travel through the vacuum space, and these waves can now enter our atmosphere in the form of many kinds of radiations, for example, light. The third statement is the speed of light is the same as the speed of electromagnetic waves. So all of the waves in the electromagnetic spectrum, which I will be showing you later, the speed of them, the speed of, for example, infrared, is equal to the speed of light. And lastly, light is a form of electromagnetic radiation. So these are all the summaries of Maxwell's equation. To illustrate, so when you have an electric current flowing through a wire, it creates a magnetic field around the wire. This idea is basic in your electricity and magnetism subject. So the stronger the current, the stronger the magnetic field. And that is present in a machine called motor. Maxwell's theory says that electricity and magnetism are two sides of the same coin, meaning electricity and magnetic fields are always created together. Here's the electromagnetic spectrum. So we can see here the types of electromagnetic waves and their names. This shows the full range of electromagnetic waves from low energy radio waves all the way to high energy gamma rays. What's interesting is that all these waves are really the same thing. They're just electromagnetic energy at different frequencies and wavelengths. And that's why we have a specific name for a specific frequency and specific wavelength. For example, we have the names radio waves, which the size of its wavelength is equal to that of a building. Microwave, infrared, the visible light, ultraviolet rays, X-rays, and gamma rays. Among all of these waves, the only visible wave detected by human eyes is the visible light, which is Well, you are very well familiar with the colors of the rainbow, Roy-G-Biv, Roygbiv. So, starting from radio waves have the least energy, and gamma rays have the most energy. From left to right in this picture, um, the pattern is from going from left to right. The more energy will the waves have or possess. The next foundation is the black body radiation. Now that we've seen electromagnetic spectrum, let's move to this concept. So what exactly is a black body? A black body is an idealized object that absorbs all electromagnetic radiation that falls on it. It's a theoretical object that absorbs all the electromagnetic radiation that hits on it. Remember the electromagnetic radiation in the previous slide? All of them, when they hit a black body, all of them will be absorbed. Nothing is reflected, nothing is transmitted. Even though a perfect black body doesn't exist in real life, the idea is really helpful for understanding how real objects emit and absorb radiation. So, what is now a black body radiation? If there is a black body, there is also a black body radiation. Black body radiation is the light, electromagnetic radiation that is emitted by a hot object. It's basically the light or electromagnetic radiation that a hot object gives off. All objects emit this kind of radiation, but the hotter something is, the more energy and light it gives off. That's why heated metal, for example, glows red, then white as it gets hotter. The color of the light that is emitted by hot metal depends on how hot it is. If the metal is hot enough, it will and it will appear as white. And black body radiation is similar to the light that is emitted by a hot piece of metal. All objects emit black body radiation, but the amount of light that it is emitted depends on the temperature of the object. Again, the general rule, the hotter the object, the more light it will emit. Just like in stars, hotter objects emit shorter wavelengths of light, which is why they appear blue or white. In your astronomy subject, we've learned that stars that are colored white or blue, they are hotter than stars that are colored red. Cooler objects emit longer wavelengths of light, which is why they appear red or orange. And now let's look at Planck's theory of black body radiation from 1900s. Planck discovered that the amount of light a black body gives off depends on two things. The first one is temperature, and the next one is the wavelength of light. So Planck showed that the amount of light emitted by a black body depends on the temperature of the object and the wavelength of light. This idea was groundbreaking because it showed that energy is emitted in small, discrete packets, which he called quanta, or quantum in singular, and not in a continuous flow. Discrete meaning not continuous. Max Planck proposed that energy is quantized, which means it can only exist in certain discrete amounts. This was a radical departure from classical physics, which assumed that energy could be continuous. And that's why we get into the quantization of energy. In simple terms, energy doesn't flow continuously. It comes in specific fixed amounts or levels. Energy is quantized. Electrons in an atom occupy specific energy levels or shells, and they can only exist at these defined levels and cannot reside in between them. It's either in the one level or the other level, not in between. There's no in between. When an electron gains energy, it can jump to a higher level. We call that excited state. Conversely, when it loses energy, it falls back to a lower level, and this often emits a photon in the process. So inside an atom, if you can imagine, electrons can only occupy these define energy levels. It's just like a kind of steps on a ladder. They can exist in between. They can't exist in between. Remember, when an electron absorbs energy again, it can jump to a higher level. That's what we call excited state. And when it loses energy, it falls back down, releasing energy as photon. If you imagine inside the atom, electrons reside in a specific level. And this is just like, by analogy, a step in a ladder. You can only go up or down the stairs one step at a time. You can go up or down half a step. And this is like quantization. Planck's theory says that energy is also like a staircase. You can only have a certain amount of energy, like 5, 10, 15. These are discrete amounts of energy. You cannot have 4.5, 4.52, 4 and a half, 4 and 3/4, 9.2, 9.1, and whatever decimals that you can pair with a whole number. You cannot have um, energy doesn't exist like that, in short. It only exists in a certain amount of energy. Actually, no. This theory, the idea behind quantum theory, it has been one of the most radical things that appeared in the early 1900s. This is a picture showing the Slovak Council Conference 1927, and we can see here the persons or the scientists behind this idea: Planck, Einstein, de Broglie, and Heisenberg. Speaking of Albert Einstein, let's move to the idea of photoelectric effect. This was Einstein's Nobel Prize winning discovery. So he used Planck's theory of quantization to explain the photoelectric effect. This is a strange phenomenon. When light shines on a metal surface, it can actually knock electrons out of it. So basically, light acts like it's made of tiny energy packets or photons. And when one of those photons hits the metal with enough energy, it ejects an electron. Speaking of photon is a discrete packet of electromagnetic energy exhibiting both particle and wave characteristics. It comes from the ancient Greek word phos or photos, which means light. It's an elementary particle in the standard model particles, which we will discuss later in this course. It is massless and it always moves at the speed of light measured in vacuum. So the modern photon concept originated during the first 2 decades of the 20th century. And this is starting with the work of Albert Einstein, who built upon the research of Max Planck. To explain the photoelectric effect, Einstein introduced the idea that light itself is made of discrete units of energy. Imagine a beam of light coming from a desk lamp. This beam of light is actually a stream of photons. And each photon is equivalent to a specific amount of energy, discrete amount of energy. Einstein's explanation of the photoelectric effect is based on the idea that light is made up of packets of energy called photon. Each photon has a certain amount of energy which depends on the frequency of the light. So energy depends on the frequency of light. So when a photon hits an electron in a metal, it can transfer its energy to the electron. If the photon has enough energy, the electron can be ejected from the metal. As you can see here, photons hitting the electrons in the metal, and if that energy is high enough, then the electron can be ejected from that metal. Again, let's just look back. What happens when light shines on a metal? So again, photons collide with the atoms of the metal. If photon's frequency is sufficient to knock off an electron, the collision produces the photoelectric effect. So Einstein proposed that energy of the light must be greater than or equal to a certain threshold energy in order to eject an electron. Lower energy means um, it cannot eject um, electrons. The energy that a photon must possess should be greater than or equal to a certain threshold of energy possessed by the electrons. So, what was the importance of photoelectric effect? Einstein's theory of the photoelectric effect was the first experimental evidence that light was quantized. Remember Planck's idea? So his formulation, which includes Planck's constant, established the relationship between energy and frequency. In this equation, energy is equal to Planck's constant multiplied to the frequency of light. So E is equal to H, which is 6.63 times 10 raised to negative 34 joule times second multiplied to the frequency of light. Example, let's calculate the energy of a photon with a frequency of 5 times 10 raised to 14 hertz. So the solution is we just simply multiply this frequency to Planck's constant, 6.63 times 10 raised to negative 34, giving us 3.315 times 10 raised to negative 19 joules. So remember, the unit of energy in physics is joules. The energy of a photon with a frequency of 5 times 10 raised to 14 hertz is 3.315 times 10 raised to negative 19 joules. The energy of radiation absorbed or emitted is directly proportional to the frequency of radiation. So the energy of the radiation is expressed in terms of frequency. The threshold frequency varies with material. Therefore, it is different for different materials. So it depends on the material, in short. So, and that's it for our discussion. Quantum theory explains behavior at the atomic and subatomic levels. Energy is quantized, it comes in discrete packets. Light has both wave and particle properties. Classical physics cannot fully explain atomic phenomena, and quantum mechanics bridges that gap and shapes modern science. Quantum theory may seem abstract, but it's what helps us understand that the invisible world that drives so much of today's technology. Thanks for watching, and I hope this helped make quantum physics a little clearer and more understandable.
苦くて黒い飲み物なんだ